Hi, I'm Julian Togelius, and I'm speaking to you from a recording because I'm hiding out in my little cottage, not too far from Copenhagen, but enjoying vacation. So um, I'm happy that you all can make it here. I'm going to talk about procedural content generation via machine learning. I represent New York University and, of course, also Model AI, which is a sponsor of this event. So, the premise of this talk is that machine learning is everywhere, but not in procedural content generation. This slide was supposed to have nice images showing various applications of machine learning, and in particular, generative methods such as generative adversarial networks, which are widely used for generating images of people and airplanes and cars and everything, and also um, uh, for generating audio, fingerprints, and a lot of different kinds of content. You can train it on. We have been able to train machine learning methods to create a number of different types of artifacts, but weirdly enough, when we talk about procedural content generation, machine learning doesn't come up much. Why is that? So, the way I see it, there are a number of different ways of creating game content generators. And at this point, I've made several of these taxonomies. Let's look at one of the simplest one there is. Basically, almost everything that people do and refer to as procedural content generation is that they design sets of rules by hand. These we call constructive approaches. So this includes the things people do specifically for particular games, such as generating pattern databases that create levels for Spelunky, for example, or for whichever game you have, or like these fancy things like Perlin noise or Cellular Automata and grammar expansion rules and so on. These are all methods where you create the rules and you run the whole system once and it outputs the content you asked for. And then we have the other family of search based and solver based approaches. So this includes things that use evolutionary computation and constraint satisfaction with all kinds of fancy computer science methods. Here, what you're doing is you're creating objectives and constraints and the representation for the content by hand, and then you use some kind of search. Obviously, a lot of the academic research has focused on the second part here. So, what's not been done very much is to not do the construction of either rules or representation by hand, but learn it. So, learn it from something that's already there. So, what we call procedural content generation via machine learning is exactly this. The basic idea is that you train machine learning models on corpuses of existing content, and then you use this to generate new content. So, there are a number of different methods for this. I'm going to give you a couple of examples, including n-grams, Markov chains, and various deep learning approaches. We wrote a survey paper on this, which came out last year in what was then IEEE Transactions on Computational Intelligence and AI in Games, which is now IEEE Transactions on Games. So we had discovered that several of us have started working in this direction independently and had done various work on trying to train different, very different types of machine learning methods on game content and make it spit out new content. So I'm going to give you a few examples from this paper specifically, which will just pool their efforts and try to sort of describe different examples and come up with a little taxonomy. It's a useful paper. Interestingly, things have already moved on from this paper, as you will see. Let's start with something very, very, very simple. So this is something I did with Steve Dahlskog, my PhD student back then, and Mark Nelson back at IT University Copenhagen. So we tried using n-grams. N-grams are some things which is so simple that it was proposed by Shannon in, I think, his master's thesis or something like that, doctoral thesis. And it was widely used for natural language processing before the advent of modern deep learning methods for natural language processing. The idea is that you capture statistic co-occurrence of sequential characters. So in natural language processing, you feed it a text, and it creates a set of tables. So the set of tables of 0 grams are the set of tables of is simply the frequency table of all the letters in the text. So if you feed it some typical English text, you'll see that some letters are more common than others, and they'll have more common frequency, and like letter D is going to be much more common and higher frequency than the letter Q or something. And this is what your predictive text methods for your old style feature phone you had 15 or 20 years ago was based on. It was based on obviously not only 0 grams, so you have, for example, 1 grams, which captures the co-occurrence of pairs of characters, 2 grams, which captures the co-occurrence of 3 characters in a row, and so on. So our idea was that, wait, we can see game content as a string, because a lot of game content only sort of appears to be 2D or 3D. It is actually largely a one-dimensional affair. So with this very, very, very simple method, we trained n-grams on the on 20 out of the 32 or something levels from the original Super Mario Bros. Game. So we did not include the castle levels, not the underwater levels, and so on. And what we got here was that we pretty easily could reconstruct things that look like Mario levels. And you can tweak the n here. So if you have an n equals 1, you have a lot of disjointed parts. If you have an n equals 2, you see some kind of structures emerging. You have the stairs and so on. And n equals 3, you get things that pretty much look like Mario levels. Maybe not the most exciting ones, but unmistakably in the style of the original Mario game. A crucial detail I forgot to mention here is the representation. So how did we make these levels into a string? Well, we had already noted in some of our previous work that you could easily see, sort of find 25 different slices or columns. We also call them micro patterns. Which together make up for about 95% of Mario levels. So basically, these are made into strings by moving along the x dimension. And as you see at the level at the top, you see or level at the bottom, you see 4 instances of just like having a little bit of ground at the bottom. And then you see, and so that's the same thing repeated 4 times. And then you see one instance of having ground with 4 blocks on top of it, and that's another, that becomes another character, and so on. So we map each one of these to a character, and then we get an alphabet with about the size of the English alphabet, where each string describes a level, and we simply run n-grams on them. Problem with this approach is that it's very data hungry. It doesn't generalize well for higher sort of level numbers of n. So for example, if you give it an n equals 4 or 5, then it will largely reproduce complete chunks of an existing level. And then when it can't find a particular n-gram, it will sort of fall back to a lower dimensional n-gram and fall into the track of reproducing part of another level. But with more data, this could of course be different. But as we will see, the lack of data is a recurring theme in many of these approaches. Another approach, which we used in a paper led by Amy Hoover, with me and Yorgos Yanakakis on as well, was that we tried to evolve the weights of neural networks to reproduce the dependency of different parts of a Mario level on each other. So it is neuroevolution, but we use neuroevolution in a supervised learning way. The idea here, taken from Amy's previous work, was that you could see different types of items in a level as different voices in a musical recording. So Amy had previously used neuroevolution to learn to predict, for example, the vocal lead melody from the drum and bass line of a song, or the other way around. So you have several different voices and you can predict the missing voices. The idea here was that we could predict, for example, the platform sizing from the ground and the positions of piranha plants and Koopas and so on. This worked to some extent. It suffers from a lack of data, of course, and there were possibly other problems here as well. So the output was never very convincing, but I still believe that it's a fruitful perspective to see different voices of the game level being as something you can predict from each other. Here are more game levels. So we have the original World 1, level 1, and we trimmed away all the voices except the ground, brick, and question mark blocks. And we tried to regenerate the rest of the voices. And the result was nothing like the original level, but it was still playable and potentially interesting. This sort of approach where you predict some parts of a level from another could possibly be used in interactive editing tools. So you're editing some parts of a level and it gives you suggestions for the other parts you want in there. Moving on from seeing game levels as sequential objects to seeing them as spatial objects, we can use convolutional neural networks, which are, of course, a tool of choice for doing deep learning on images and image-like content. So if you're dealing with any kind of visual deep learning these days, the first few steps are usually convolutional nets. We thought about what we could use this for, and we thought that the natural type of content here is maps for games such as StarCraft, for example. The idea here is that a little bit similar to the previous work on predicting, for example, platforms from ground levels in Super Mario Bros. Levels. We thought we could predict different parts of StarCraft maps from other parts. So, for example, here we trained on a number of StarCraft maps, and we tried to predict where the resources, so the gas geysers and the crystal mines would be, or the crystal deposits would be from the topology of the map. So the input was a height map, the output was the positions, so 2D map of the positions of the resources. And as you can see on the side here, this worked pretty well for some maps. So the original map you see here in yellow, this was where the resource was, and if you give it if you put a threshold just right, you get resources that are essentially in the same places. You can also change the threshold of the outputs to get a more or less resource-rich map, which can be useful. The intended use for this kind of method was in some kind of interactive editing tool where you would be able to draw a map, and in real time the system would be able to tell you that, hey, maybe you should place some crystals and gas over here, or maybe this place is a good place for a base starting location, and so on. So this is a little workshop paper that is by now almost 3 years old, and the results aren't very convincing because what you're seeing here is when it worked. Very often it didn't work. we saw a lot of overfitting. Even though we tried various types of data augmentation. Yeah, sorry about that. So moving on to another kind of very, very useful machine learning method that has been used very, very widely for sequential types of data in the last decade or so. It's the long short-term memory network, or LSTM for short. So when I said before that your old feature phones from 15 to 20 years ago would use n-grams for text recognition and prediction, your fancy new smartphone from 2019 is definitely using long short-term memory for this. So LSTM networks is a specific type of recurrent neural network which can learn long time dependencies in sequences, and therefore it's widely used for predicting the next word in a sentence, and is also widely used in machine translation. And how can we do this with PCG? So we can actually go back to the idea of seeing level content as strings and use LSTMs instead. So this example is due to Adam Somerville's research and is also covered in the paper I talked about before, our joint survey paper. What Adam Somerville did was that he differed from Steve's and mine and Mark's work on using n-grams in Mario by using a different representation, a different machine learning method, and also including Mario's position in the training data. So instead of seeing each x position, or each position in the x dimension as one character, he used a snaking representation where he first walked up the first column and then down the second column, up the third column, down the fourth column, essentially. So he snaked back and forth the level, and this way he could extract a much longer string where each tile corresponds to a character. He also looked at videos of people playing Super Mario Bros. And included the position of the Mario's agent at each x position as well. This is very nice because this it teaches the network to recognize what playability is, and things such as Mario's position never changes in the y dimension, never changes drastically between one tile and the next. Using this, he fed LSTM networks this way, and then prompted them to create new levels, and got really, really good results. So better than the ones we had using the n-grams, which was sort of expected, but it's still nice to see. LSTMs can also be used for actual text. So here we have a magic card, a newly generated magic card. Magic, as you may or may not know, is a collectible card game with thousands of cards, maybe tens of thousands now, I don't know, lots of them at least. And the idea here was that he would create, it's also Adam Somerville's work, that Adam would create a system that would inspire new card designs. It wouldn't create completely functional cards on their own, but things that could easily be made into functional cards. So we trained it on a large data set of magic cards, including the text describing the effect of the card, the mana cost, the attack and defense value, and so on. So in this case, we fed the mystical tutor, as called, with the instructions that it should be a legendary card and it should be a fungus shaman. And what comes out is creature which has the following description. Whenever a creature enters the battlefield under your control, you may put a 2/2 green wolf creature token with haste onto the battlefield. Now, maybe your first reaction is that, wow, that's perfectly legible English. It's a correct sentence, and it even sounds very much like a parsable text on a magic card. So the procedural generation works, in other words. However, when you look closer at it, you realize that this is an absolutely unplayable card, it's game breaking, because what happens is that you can create a new green wolf creature when you play it, but that's a new creature, so that allows you to put a new green wolf onto the battlefield, and so on. So you get an arbitrary amount of green wolves, as many as you want, and they all have haste, meaning that you can essentially win any game instantly using this card. So the card is broken, but is interestingly broken. You could easily take this specification and make this into a more usable card that would actually fit in the game. Now, next is what you've all been waiting for, because when you hear about machine learning and generating things, what you think of is, of course, generative adversarial networks. So generative adversarial networks, since they were invented by Ian Goodfellow in 2014, they've stolen all the hype, not all the hype, but a lot of it. And they indeed are very, very impressive. The core idea is you train two networks intermittently, a generator and a discriminator. So the discriminator is trained to distinguish real artifacts from fake generated ones, and the generator is trained to generate artifacts that fool the discriminator. So for example, to train a generative adversarial network, or GAN for short, on a set of images, you first have a discriminator that just produces noise, nothing useful, and you tell, or a generator network that produces noise, and you tell the discriminator to learn to distinguish the real faces from the noise, which is easy. Then when you've done that, you then tell the discriminator to learn to produce images that can fool the discriminator that they are faces, which is also sort of easy, because at that point the discriminator network is very primitive, and you keep doing that again and again, and it's hard to do, and it breaks down, and you get mode collapse and all kinds of weird things happening. But if it works, you now have a network that can reliably produce nicely looking faces that can fool humans as well. So the schematic of what happens here is that you have a training set, you put them into the discriminator, and it tells you whether it's real or fake, and you have a generator that outputs fake images, and which is trying to fool the discriminator. A crucial detail here is the random noise input to the generator, which is also called the latent variables. We're going to get back to the latent variables, because the random noise are meant to be random noise, but you can also do different things with what's called the latent input. Now is where this talk gets more provocative, or more conceptually provocative. So when you look at what GANs and other things like autoencoders, variation autoencoders, and there are a number of other kind of machine learning methods that can be used for this, have been good at producing, these are images of various things, and these are also sounds and maybe maps and so on. But there's all the kind of content which it doesn't matter too much if there are some slight imperfections in it. Language models, for example, they are, I don't know if you've seen the blog post from OpenAI about better language models and their implications. If you haven't, you really, really should read it and read the examples of generated text. And you find things which is like, on a surface level, it's very, very good English, and it sounds like real. It sounds like a real story that someone has written. But when you dig into it, there isn't really coherence at the end of it. So the question is, are these methods good enough to use to generate game content? Or does game content have the kind of properties that make it amenable for machine learning generation? And I would claim that it doesn't, because a game level is in some ways much harder to generate than a picture of a face. Now, if a face is slightly off and one eye is like a little bit closed, and the background has strange colors and the hair is a bit fuzzy, that doesn't matter much. You still recognize it as a face. But for a game level, it has the properties of an image. It needs to be nice to look at, have balanced color, have the right geometry, be readable as a game level. But a game level is also in some ways like program code. You know, a game level which you can't finish, it's not like a nice game level with an imperfection. It's broken, cannot be played. And a game level that has a complete obvious exploit, like, well, you can also just walk left and then you win the level. That's also broken. Its value is essentially zero. So it's so in many ways, game level is like program code. It needs to work, which makes it very different from an image of a face, an image of a car, or a sound, or something like this. You can also say that a game level is like an ecology. There's so many things that need to be tuned just right, because it's no good if it's like there's a long stretch of nothing happening, unless you meant for it to be a long stretch of nothing happening. It's no good if some challenges are ridiculously complex compared to some other challenges, and so on. So game content, I would argue, not just game levels, but characters, quests, and whatever you try to generate, have a lot of properties that make it much harder to generate these things than typical machine learning. And if you train a GAN on a lot of game levels and just make it output new game levels, most of them are broken. So, I mean, we tried. It's you can try it for yourself. It doesn't just work. And this is something that many people think or don't appreciate enough, I would say. So what can we do? So one very, very clever idea is to combine learned models with search. So basically, combined procedural content generation via machine learning with search-based procedural content generation, or combining PCGML with SB-PCG. The idea here is that you have a model that generates game content, and it takes some kind of input, preferably a vector of real numbers, and then you can search this input space for good content. So the objective function uses the model to transform from input to output. In search-based PCG terminology, the machine learned model becomes the representation you use in your search algorithm, so the content representation. Let's show you an example. This is a very, very good paper by a bunch of my friends, which takes an approach that we developed for generating fake fingerprints and applies this to Super Mario Bros. The idea here is to train a generative adversarial networks, as we talked about before, to generate new Super Mario Bros. Level segments, and then to evolve the inputs to the latent space, the latent variable input, to get levels with particular properties. And this is a very, very powerful approach. So the two steps are summarized here. First, you use real levels and take real samples of the real levels, feed it into the discriminator, train a generator to generate new level segments that could fool it. And the input to the generator at this point is just Gaussian noise, as it would be with a typical generative adversarial network. Once you're done with this, then you use an evolutionary algorithm, in this case a CMA-ES, to evolve new inputs in the latent space. And the fitness is how well the generated levels fulfill certain criteria, which are tested with a Mario playing agent that plays the level. For example, it should be playable, maybe it shouldn't be too easy, and so on. And you can use Mario playing agent and do this. I think they used Robin Baumgarten's classical A-star agent in this case. We see the architecture up here. It's a fairly standard convolutional deconvolutional generative adversarial network, DCGAN. And you see the difference here in the two rows that if you do random sampling, you get various level segments which may not look super interesting. Sometimes they're broken, most often not broken. You also see that you have a high degree of locality in this representation. So if you take the parent in the second row to the right, you take a parent input and do small numerical mutations, you see that those come out to looking something very much like the parent with small differences. So this is a very, very nice representation in search-based PCG terminology. Here's some examples of what can be evolved. Playable level, maximizing jumps. Playable level, minimizing jumps. These are the two top ones. And then we have an unplayable level. It is indeed looks very unplayable to us. And one with broken tiles. You see the pipe is like completely wrong in various ways. And this is a level with increasing difficulty. Starts out easy and then and then gets harder and harder. How this happened is that they produce different levels, different level segments, and tie them together. So this is a really cool approach, and this could be done with many other things as well. Now, I've given you some examples of what works. So let's talk a little bit about what doesn't work and what the problems are. So in much of PCGML, we have this issue that output is not, it's pretty, but it's not correct or balanced. So you saw the magic card that looked all right, but was like not really playable. And you saw that these Mario level segments that had missing tiles and so on. So it's not really it's not really as it should. And it's as I said, I mean, people don't publish these results. Just using a GAN, for example, on a level and getting random outputs, most of it is not playable. So combining procedural content generation with search-based PCG helps a lot. And this is something that you should be looking at if you're thinking of using machine learning in the PCG. The other two examples are amount of training data and diversity of output. So the training data problem is that each game really only has so many levels, and for other content the same true. You have so many characters, so many quests and so on, because it's expensive to author things by hand. And very often the amount of data in a particular game makes for a pretty small data set in normal machine learning terminology. And very often this content is not even available without manual extraction, because you can't just easily extract it from a game. A nice thing is that there are lots of enthusiasts that sit and transcribe levels and maps and so on from games. But the problem is that if you want to do PCGML for a new game, how are you going to do this if you don't have any content to train from? And even if you want to do it for an existing one, you sort of face up to the problem that you don't really have much to train from, so you're going to get a pretty limited representation. So grand challenge for PCGML, as I see it, is to learn reusable representations from the content in multiple games and fine-tune on new games. So, for example, in language models, you can train language models on lots of text of different kinds and maybe in different languages, and then you can fine-tune on a small amount of text in a new style and get very good output. I wonder if you could do something like this for PCGML. Train a model on all the platformer games and learn how to produce content. Fine-tune it on just a few levels of a new game that's under development, so you see what kind of stuff is in there, and then generate new content that works with that game. I'm not entirely sure how to do this, but this is something I see as a grand challenge with PCGML. One approach to deal with the content shortage problem is bootstrapping. So assume we can test a level if a level is good enough using some constraints. What we can do then is that when the level is good enough, we can put it back into the training set and train more. In fact, we did this already. in a collaboration with Sebastian Risi and Ruben Rodriguez Torrado. In my lab is the first author of the paper. It got rejected from 8, but we are touching up the paper and resubmitting it. We'll also put it in archive as soon as possible. Isn't it great with peer review? There's like nice randomizer on all your scientific output. You never know if you're just going to get accepted. Anyway, this is another good idea that I think will be used more in the future for those cases where you can easily test, for example, playability. So this allows you to sort of grow from a small initial data set to a larger one. Another problem is the content diversity problem. So if you train a model on n data points, so n levels, mostly the samples from this model are going to be inside the convex hull formed by these points. So it's going to be some interpolation between the existing levels mostly. And the big problem here is, how do we create new content that is actually novel, that doesn't just feel like it was something that came between the previous levels we trained on. Levels or characters or quests or maps or whatever. One approach here, this is a paper from 2013, which I think includes a number of good ideas that could be worked on. We call it Delonox, the Deep Learning Novelty Explorer, is to interleave exploration and transformation. So you put the levels in this game, or in this case we did spaceships. We trained an autoencoder on these spaceships. Now we could sample by inputting random noise into the autoencoder middle layer and get new spaceships out of it. But instead of doing randomness, we explored. We used novelty search, so a quality diversity algorithm, to find output that were as far as possible from the stuff that the autoencoder had trained on. So output that had maximum reconstruction error. This is a way of basically finding the boundaries of the model you learn and intentionally pushing the boundaries. And it's something that is an approach that might be useful for finding game levels that are more diverse. Speaking of novelty search is a type of quality diversity algorithm. Quality diversity is this new class of search algorithms that place arguably more emphasis on exploration and optimization. So for example, Map Elites is a quality diversity algorithm that we've been using a lot in recent research in my lab, where you find a map of all the solutions that vary according to certain dimensions, and the best solution you can find for each setting, or for each sort of dimension. So this gives you not just a good solution, but a whole map of good solutions, a map of the elites, so to speak. I think there's a lot of potential in combining this approach with procedural content generation through machine learning. Now, in this paper, the survey paper I mentioned in the beginning, we did a little survey, as it was a survey paper, did a survey of what kind of different data representations, graph, sequence, and grid, and what kind of machine learning method had been used for each of them, and then we try to map like how the studies have existed, and it shows that there is a lot of virgin territory. There's a lot of like types of machine learning and types of that just haven't been applied to different kind of game data. So there's a lot for you to just go out there and grab and try to apply. So where do you get the data from? Well, the video game level corpus, VGLC, is very good. It has data from a couple of games, but it has it in a unified format, which I think is very good. The new Mario AI framework, which is not Mario.org, it's marioai.org, is also very useful for this, as we have a new format for the levels, and we include a bunch of levels in both the real ones, where they were made by real humans, and those made by a number of different PCG approaches. Lots of games have fan sites, mods, and wikis. And for example, if you go to Candy Crush, which may or may not be a favorite game, you'll find that some people have somehow transcribed all of the thousands of levels in the game, and you can just find them in a nice picture format, which you could easily parse yourself. So you might want to go out and look for level data or other kind of game data, quest data maybe in that way as well. Finally, I would, of course, not urge you to hack Super Mario Maker and make the levels publicly available, because that would be an incitement to criminal activity and I would get sued by Nintendo. So I'm clearly not urging you to do this. Oh, of course, don't do this. But but if you do, let us know. That would be some pretty sweet data to look at. Finally, machine learning is an enormous field. There's so many approaches, there's so many clever tricks and everything. In particular, in supervised learning and self-supervised, which is what we have talked about today, which is I am aware of, clearly not the only type of machine learning out there, but that's what we talked about today. But nothing of what you see, for example, has used any clever regularization methods and pretty basic data augmentation methods and so on. So there's a lot of data out there, and there's a lot of methods out there. So go forth and try all the clever tricks. I think there's a lot of good work to do here. That's it from me for today. I hope it gave you some interesting thoughts. Well, let's talk more about this when I see you next time.